Hello everyone, welcome back to my YouTube channel. You have probably used ChatGPT or heard about Gemini or Claude. But have you ever stopped and asked, how does this thing actually work? How does it understand what I am saying? How does it write back like a human? Today, we are going to answer that completely. No assumptions what about you already know. Even if you have never studied computers, programming, or AI, by end of this video, you will genuinely understand how large language models work. So, what is LLM? LLM stands for Large Language Model. So basically, large means these models are enormous. They learn from hundreds of billions of words. Language, they work with text, they read it, they understand it, and write it. Model, it's a mathematical system, a very sophisticated one. An LLM is a computer program that has read massive chunk of internet, books, articles, Wikipedia, code, conversations, and learned patterns from all of it. So when you ask it a question, it uses those patterns to write a smart answer. But how does it read text? Because computer don't understand words. They only understand numbers. And that is exactly where we begin. Step 1, tokenization. Before the model can do anything at all, it needs to convert your words into something a computer can actually process. Numbers. This happen in two steps. First, tokenization and second, embeddings. Let's take them one at a time. Imagine you type this sentence, hello, how are you? The model does not see it as five words. It breaks them into pieces called tokens. A token is roughly a word or part of a word. Hello is a one token. A comma is its own token. How are you? Each their own token. But longer or rare words get split further. For example, unbelievable might become two tokens, un and believable. Why? Because it's more efficient. The model works with pieces it already knows. Now, every single token gets replaced by a number. This number is its ID from a fixed list called the vocabulary. So, hello might be number 15496. The comma might be 11. How might be 890. So, your sentence, hello, how are you, becomes a list of numbers. That list of numbers is what actually goes into the model. Computers love numbers. That's the whole point. But here is the problem. Just because cat is number 500 and dog is number 501, that doesn't mean the model knows that they are related. They are just two numbers sitting next to each other. There is no meaning in that. We need something smarter, something that captures what words actually mean and how they relate to each other. That's where embedding comes in. Embeddings. This is where meaning enters the picture. Think of an embedding like giving every word a location on a map. But instead of a normal 2D map with just X and Y coordinates, this map has hundreds of dimensions. Every word gets placed at a specific location in the space based on its meaning. And here is the beautiful part. Words with similar meanings end up close to each other in this space. Look at the slide. Dog and puppy are very close to each other. Both are animals, both are pets. Car and vehicle are close, same concept. But dog and car are far apart, nothing in common. Each word's location is stored as a long list of numbers, which is called as a vector. So dog might be 0.21, minus 0.45, 0.33, and so on, going on for hundreds of numbers. Each number captures a tiny aspect of word's meaning. These embeddings are not hand programmed. The model learns them automatically during training just by reading enormous amounts of text. Here is the example that blows everyone's mind and it's real. If you take the location of the word king in the vector space and subtract the location of man and add the location of woman, you land almost exactly on the word queen. King minus man plus woman equals to queen. The model figured out the concept of royalty, the concept of gender, the relationship between them, all just from reading text. Nobody programmed this, it emerged on its own. This is the power of embeddings. Words are no longer just numbers, they have geometry, they have meaning, they have relationships. And these embeddings are what flows into the next part of the system, the neural networks. the processing engine basically. The name neural network sounds intimidating, but it's not. Let me use a simple analogy. Imagine you're teaching a child to recognize a dog. You show them 1,000 photos. This is a dog, this is not a dog. Over time, the child's brain adjusts. It starts noticing patterns, four legs, fur, a tail. They get better and better. A neural network does exactly the same thing, but with mathematics instead of a brain. Look at the side on the left. You have input nodes. These receive the embedding vectors. In the middle and the hidden layers, where the actually processing happens, on the right is the output. Each connection between nodes has a number called a weight. It controls how much influence one node has on the next node. Initially, all these weights are random. The model is terrible, but during training, they get adjusted again and again until the model starts making good predictions. We'll cover training in detail shortly. Now, here is the important limitation of basic neural network when it comes to language. A standard neural network processes each word separately in isolation. It has no natural way to understand that words in a sentence are related to each other. For example, the trophy didn't fit in a bag because it was too big. What does it refer to? The trophy, the bag, you knew instantly, the trophy. But a basic neural network struggles because it looks at each word separately without considering the full context. This is exact problem that led to biggest breakthrough in modern AI. So, in 2017, researchers at Google wrote a paper called Attention is All You Need. It is not an exaggeration to say this single paper changed the entire direction of AI. They introduced a new architecture called the transformer, and the key idea inside it, the idea that solved our context problem, is called attention. Attention allows the model to look at every word in a sentence at the same time and figure out which words are most important for understanding each other. Instead of reading word by word like a basic network, the transformer reads the entire sentence at once and draws connections like a spider web linking related words together. Let's see attention in action with our example. The trophy did not fit in the bag because it was too big. When the model processed the word it, the attention mechanism asks which other words in this sentence should I focus to understand what it means. It gives each other words a score, a number representing how relevant that word is. Look at the slide. You can see the arc connecting it to trophy. That thick bright line represents a high attention score. The model has learned that it is most strongly connected to trophy. So let's say trophy gets a score of 0.82, very high. Back gets a score of 0.29. The gets almost nothing, 0.15. So now the model blends information from all words weighted by these scores. The result is that it now carries meaning from trophy. So the model correctly understands it means the trophy. This happens for every single word in the sentence all at once in parallel. That is self-attention. Now, how does this model actually calculate those attention scores? This is where the Q, K, and V come in. Three letters that are actually machinery behind attention. Don't let them scare you. I'm going to explain each one with a real world analogy that makes it completely simple. Imagine you walk into library. You go to the librarian and say, I'm looking for books about space travel. That request you just made, that is the query or queue. It's what you are searching for. Every book in library has a label on its spine. Science fiction, history, physics, those labels are the keys or K. They describe what each item contains. And the actual content inside that book, the words, the knowledge, that is a value or V. So the attention mechanism does this for every word in a sentence. For each token, the model creates three things. A query. What is the word looking for? A key. What does this word offer to others? And a value. What is the actual content this word carries? Now look at the slide. The token embedding, that vector of numbers, enters from the left. It gets multiplied by three separate learned weights matrices. WQ, WK, and WV. Each multiplication produces one of the three vectors, Q, K, or V. These weight matrices are learned during training. The model figures out on its own the best way to generate the Q, K, and V for every token. Now, here is where it gets really powerful. The model does not do this QKV process just once. It does it multiple times in parallel. Each time is called as a head. Yes, the slide shows four heads: head 1, head 2, head 3, and head 4, each running their own separate Q, K, and V calculation simultaneously. So, why we require multiple heads? Think of it like having four different expert readers look at the same sentence. So, reader 1 notices who is doing what to whom, the grammar. Reader 2 notices which words share the same topic. So reader 3 notices this word is referring back to something mentioned earlier. And reader 4 notices the emotional tone of these words. So each head notices something different. Each learns a different type of relationship between the words. After all the four heads finish, their outputs get combined. Look at the bottom of the slide, you can see the concatenate box. All four outputs are joined together and pass through one final layer to produce a single rich output. So the result is incredibly detailed understanding. The model sees the sentence from four different angles at same time. And just to put the scale in perspective, GPT-3 does not have four heads, it has 96 heads across 96 layers. That is why these models are so powerful. And here is the actual mathematical formula that makes all of this work. I know it looks intimidating, but I'm going to walk you through it piece by piece. And I promise by the end of this slide, you will understand every part of it. So the formula is attention of Q kV equals softmax of Q times K transpose divided by square root of dk multiplied by V. Let's break that apart. Q times K transpose. This is comparing every query with every key. So remember the library. This step is like checking how well does my space travel request match each book's label. So the result is a score for every word pair. How much should this word attain to that particular word? Divided by square root of dk. Now dk is just the size of the vectors. So we divide by this to keep the numbers from getting too large. When scores get too big, the maths become unstable and the model stops learning properly. So this tiny division keeps everything balanced. That's all it does. Softmax. This takes all those raw scores and converts them into percentages. That adds up to 100%. So instead of messy numbers like 8, 2, 1, you get clean percentages like 80%, 15%, 5%. Now you have a clear picture of exactly how much attention each word deserves. Multiplied by V. Finally, you use those percentages to take a weighted mix of values. Words with high attention contribute more to the output. Words with low attention contribute less to the output. So the result is an representation of each word. One that now carries information from words it was paying attention to. So that one formula right there on your screen is the heart of every major AI language model in the world. ChatGPT, Claude, Gemini, all of them built on this particular formula. So now the model understands which words relate to each other, thanks to the attention. But there is one more problem where we haven't solved it. Read these two sentences carefully. The dog bit the man bit the dog. Same exact words, completely different meaning. The only difference, the order of the words. So here is the problem. Attention by itself does not care about the order. It looks at all words at once and finds relationship. But it treats the sentence like a bag of words thrown on a table. So it doesn't know which word come first or last. So without any fix, the model will think those two sentences mean the same thing. That's a disaster. This is what positional encoding solves. Look at the left side of the slide. Those colorful wave patterns. Those are sine waves at different frequencies. One wave per position in the sentence. So here is the idea. For every position, position 1, position 2, position 3, and so on, we generate a unique patterns using these waves. Every position gets its own fingerprint. No two positions have the same pattern. Think of it like a seat number at a cricket stadium. So every seat has a unique number. The seat number tells you exactly where you are without needing any other information. So positional encoding gives every word its own unique seat number directly into its vector. Now look at the right side of the slide. You see three columns: token embeddings, positional encodings, and the resulting combined vector. The step is beautifully simple. You take the words meaning vector, the embedding, and you add the position vector to it. It is just an addition, nothing else. So the final vector for each word now carries two pieces of information at once. First, what the word means, and the second, where in the sentence it appears. Now, dog at position 1 and dog at position 4 have slightly different vectors. So the model knows they are the same word sitting in different places. So this is just the recipe of generating those unique wave patterns. You don't need to memorize the formula. What matter is what it does. Creates a unique smooth signal for every position. And because it uses smooth wave functions, the model can even handle sentence lengths it has never seen before. So before the transformer layers even begin processing, every word has two things added together. Its embedding capturing its meaning, its positional encoding capturing its position. So the model now knows what every word means and where the every word sits. Only then does the real processing begin. The next is training. This is where the model actually learns anything. Here is how training works. You take a massive amount of text, hundreds of billions of sentences from internet, books, Wikipedia, and more. You hide the last word of every sentence and ask the model what word comes next. For example, the cat sat on the dash. So the model guesses maybe it says floor, but the correct answer is mat. So the model was wrong. So the system calculates exactly how wrong. This is called the loss. Then it works backwards through all the layers and makes tiny adjustment to the every single weight to make the better guess next time. This process is called as backpropagation. It does this billions and billions of times. Look at the slide. You can see the full loop. Text corpus goes in, tokenizer breaks it up, transformer model processes it, predicts the next token, calculates how wrong it was, and the back propagation adjusts all the weights. The loop repeats again and again. After enough rounds of this particular thing, the model gets extraordinarily good at predicting text. But the more important thing is to predict the text well, it has to understand the meaning, grammar, the fact, the context, and even some reasoning. So predicting text is the training task, but understanding language is what it learns as a result. This pre-training runs for weeks on thousands of powerful computers, but it costs millions of dollars. That's why only a few companies can build these massive models. This is nothing but the pre-training. Pre-training makes the model a great text predictor, but that does not automatically makes it a great assistant. So a text predictor might complete your sentence in weird or unhelpful way. So there is a second phase called as a fine tuning. So where the model learns to be helpful, honest, and safe. Look at the three stages on your slide. Stage one, supervised fine tuning. So human trainers write examples of ideal conversations, good questions, and good answers. So the model learns from these examples directly. Stage 2, reward model training. So the model generates multiple responses to same question. Human raters compare them and say which one is better. A separate model called the reward model learns to predict these human preferences. It learns what a good response look like. Stage 3, PPO optimization loop. Now the main model is further trained to maximize the reward model score. Every response it generates gets a rating. It adjusts it to get higher ratings over time. This is known as reinforcement learning. The same technique is used to train game playing AI. This whole process is called as reinforcement learning from human feedback. It is what turns a raw text predictor into something like ChatGPT or Claude, something that actually follows instruction, gives useful answers, and avoids harmful responses. The model is trained. You open ChatGPT, you type a question. What actually happens? Your message is tokenized and fed into the model. So the model runs it through all its transformer layers and produces a probability distribution. Basically, a list of every possible next word and chance of each one. So it picks one word, that word gets added to the input, the whole thing runs again and again, one word at a time. This is why the text appears word by word when you use ChatGPT. So the model is literally generating one token at a time, each word building on everything that came in before. This is called as auto-regressive generation. This process, auto-regressive generation, auto, meaning it feeds its own output back as input, regressive meaning it builds the answer step by step. And it does not always pick the single most likely word that will make responses repetitive and boring. Instead, it picks them from top likely words with some controlled randomness. This is managed by setting called temperature. High temperature, more creative and varied responses. Low temperature, more precise and focused responses. So when developers build apps on top of LLMs, adjusting temperature is one of the key controls they use. There is actually a few different strategies for choosing which word to pick next. Your slide shows them all. Let me walk through each of them quickly. Greedy decoding. Always pick the word with the highest probability. It is simple and fast, but it often produces very repetitive text. Temperature sampling. It adjusts how spread out of the probabilities are. Low temperature makes the model more confident and precise. High temperature makes the model more adventurous and creative. Top K sampling. It only considers the top K most likely words and pick from those. This filters out weird, low probability words while still allowing variety. Top P sampling. It is also known as a nucleus sampling. It picks from the smallest group of words whose combined probability adds up to P. This is more dynamic than Top K and it is widely used in production AI systems. So when you notice ChatGPT giving slightly different answers each time, you ask the same question. This is why controlled randomness. Now, before you think LLMs are perfect, let's be honest about their real limitations. So there are four big limitations every LLM user should know. First, hallucination. The model sometimes makes up facts confidently. It generates the statistically most likely words, not necessarily the truthful ones. If it doesn't know something, it may invent a convincing sounding answer instead of saying, I don't know. This is not a simple bug that gets patched, it's a deep structural challenge. Second, no persistent memory. Every new conversation starts completely fresh. The model has no memory of your conversation from yesterday. Within one conversation, it remembers context, but if you close the tab, it's gone. Third, limited reasoning. LLMs are extraordinarily good at patterns, but they can still fail at problems that require genuine multi step logical reasoning, especially novel problems that haven't seen patterns before. Fourth, knowledge cutoff. The model was trained on a data up to a certain date. It generally does not know what happened after that. Ask it about last week's news, it can't help you. None of this means LLMs aren't incredibly useful. They are, but knowing the limits makes you smarter, more critical user. Let's bring it all together with this beautiful end-to-end picture. This is a slide which shows you complete journey from moment you type something to the moment the model responds. Raw text comes in, tokenizer breaks it into tokens and maps them to UNA. The tokenizer breaks it into tokens and maps them to numbers. The embedding layer converts those numbers into rich meaning vectors. Positional encoding is added so that model knows word order. The stack transformer layers with all that attention magic process everything deeply. Output logics are produced, a score for every possible next word. Sampling strategy picks the next token, and that token becomes the generated output. This loop repeats token by token until the model finishes its response. Every single step we covered in this video, tokenization, embeddings, attention, QKV, multi-head attention, formula, positional encoding, training, RLHF, sampling, it's all here in this one particular diagram. This is a complete picture of how LLM works. If this video helped you understand the LLMs, genuinely understand them and not just at a surface level, please hit the like button. It takes 1 second and it helps the channel reach more students just like you. Subscribe to the channel for more such videos. Got a question about anything that we covered today? Drop it in the comments. See you in the next one.